I am Dr. Shubha, Assistant Professor who has been for past 18 years at St. Francis College for Women teaching physics and electronics for undergraduate students. I am currently Head of the Department of Electronics and Controller for Examination at our college. When I was a kid, I used to look into the mirror and was fascinated to see my image, always wondered how this was possible. As I grew up, I understood that it's reflection. This questioning nature of mine allowed me to do PG in physics. I have taught optics, thermodynamics, nuclear physics, basic electronics, microprocessors, some of the papers to name. In addition to normal blackboard and chalk approach, I use modern methods pedagogy to engage students. Some of the innovative techniques like Dept videos, YouTube videos, PowerPoint presentation, simulation software to demonstrate circuit theory, simulation software to show them programming, and the virtual labs which is designed by IITians. In addition to teaching, I also conduct annual workshops. Some of the workshops like drone technology in association with American Corner, e-Rakhi, e-Christmas tree and embedded systems to name few of them. In addition, we also organize field trips to Vikram Sarabhai Space Center, VSCC, IMD, INCOIS to name few of them. I was coordinating Spectrum Science Club in 2009, which aims to motivate students by conducting intercollegiate science fest and novel event called GLEE. In GLEE program, underprivileged school students witness laboratory experiments at our college. I was instrumental in getting many students to enroll to clear ham radio exam conducted by National Institute of Amateur Radio NIAR. I am really concerned about students' well-being. I conduct remedial classes for students who lag in performances. I conduct career counseling sessions and has been Dean Student Affairs during the academic year 2010-11. I encourage students to do projects and internships during summer breaks. I have helped students to participate in outside activities and win many prizes regularly. Two of my students have finished their PhDs from Jawaharlal Nehru Center for Advanced Scientific Research, JNCASR. I really enjoy teaching physics. It's a pleasure to teach fresh batch of students every year. Today's session, I will be talking about tunnel diode. A tunnel diode is also known as Isaki diode. This is named after the scientist Leo Isaki. This diode works on the principles of tunneling, hence it is called as a tunnel diode. In 1973, Leo Isaki received Nobel Prize in Physics for discovering this tunneling effect. Leo Isaki observed that if a semiconductor diode is heavily doped with impurities, it will exhibit negative resistance. A tunnel diode can also be called as heavily doped PN junction diode. Germanium material is commonly used to make a tunnel diode. They are also made up of other type of materials such as gallium arsenide, gallium antimonide and silicon. Now what is the difference between a tunnel diode and a PN junction diode? In a normal PN junction diode, the depletion region opposes the flow of current. Hence, depletion layer acts like a barrier. To overcome this barrier, we need to apply sufficient voltage. When sufficient voltage is applied, the electric current starts flowing through the normal PN junction diode. But in case of a tunnel diode, the P and the N type semiconductor is heavily doped, which means a large number of impurities are introduced into the P type and N type semiconductor. This heavy doping produces an extremely narrow depletion region. The concentration of impurities in a tunnel diode is 1000 times greater than that of a normal PN junction diode. Now, how does a symbol of a tunnel diode looks like? The circuit symbol of a tunnel diode is shown in the figure, and in tunnel diode the P type semiconductor acts like an anode and an N type semiconductor acts like a cathode. It is similar to that of a PN junction diode, with an extra 2 lines. Now, if you flip this diode, it looks something like a tunnel, a vehicle travelling at the entrance through a tunnel. Similarly, the electrons also tunnel through this particular tunnel, hence it is called as a tunneling diode. Now, how does a tunnel diode works? Now, let me explain this concept with the help of a Fermi band energy band diagram. Now, consider two crystals with same semiconductor material. One is doped with a trivalent impurity, hence you get a p type. The other one is doped with a pentavalent impurity, hence you get an n type. Now, what you do to this p type material is you add this material, the impurity more and more, so that the p type material becomes p plus plus, and you add more of pentavalent impurity to your n type, so that your n type material becomes n plus plus. Now, when you draw a diagram, band diagram for a p type semiconductor, as shown in the figure, it looks something like a band diagram with EV and EC, and similarly for your n type. Now, what you do is you try to dope, when you try to dope heavily with an p type, the Fermi level is no more like at the center like an intrinsic semiconductor, but the Fermi level comes towards your energy of your valence band. So, further you dope it, it goes into your valence band. In case of your n type semiconductor, since the doping is heavy, the energy Fermi level reaches to your conduction band, further doping will enter into your conduction band. For a tunnel diode, doping would be really very high. If we dope p side, it becomes p plus plus. Then in this case, semiconductor itself degenerates and the Fermi level will be close. In fact, the Fermi level will be inside your valence band. And similarly, when an n type becomes n plus plus, the Fermi level will be inside your conduction band. Hypothetically, when you join your p and n type together, there are lot of electrons in the n type which move towards your p type, and lot of holes in the p type which moves towards your n type. As a result, the diode is at equilibrium and the overall potential is equal to Q times VBI, where VBI is also called as built-in potential. Fermi energy level becomes constant throughout the diode and no current flows through it. Now, let us look into the working of a tunnel diode. The step 1 is when you have an unbiased tunnel diode. When no voltage is applied to a tunnel diode, then the energy band diagram would look something like this. This is exactly equivalent to an equilibrium band diagram. That is, the conduction band electrons at n side and the valence band holes at the p side are nearly at the same energy level. Hence, the net current flow will be 0. The second case would be if you apply a small voltage to the tunnel diode, assume it is V1. When a small voltage V1 is applied to a tunnel diode, then what will happen? How does a tunnel diode work? When there is no potential field, then there is a small built-in electric field inside the depletion region, as I have already told you, and this let it be VBI. This VBI generated is opposite to the voltage V1 applied. Hence, the electric field would decrease. As a result, the depletion width will also decrease. N-type energy band would move up and P-type energy band would move down. As a result, the potential band would be reduced to Q times VBI minus V1. That is, you would have lot of electrons and on the N side and lot of holes on the P side, and the depletion region would really become very small, because now the potential barrier voltage is given by Q times VBI minus 1. In fact, it is the amount of energy is around few nanometers. Typically, electron must, when the bandwidth is so small, it is something around few nanometers. In a normal p-n junction diode, typically the electrons must surmount through the potential barrier. Similarly, the holes must surmount through the valence band to reach on the other side. But since in a tunnel diode, these two junctions are heavily doped, instead of surmounting through the potential barrier, they tunnel through the potential barrier and reach the other side. That is, the electrons in the n-type material tunnel through the potential barrier and reach the p side, and holes in the p side tunnel through the potential barrier and reach the n side material. This phenomena of tunneling of an electron through the potential barrier is called as tunneling phenomena. So, we observed in this particular case too, when a small voltage is applied, the current starts flowing through the tunnel diode. Now, the next one is case 3, where you slightly increase your voltage much more. Let the voltage be V2. Applied voltage is slightly increased. When the voltage applied to the tunnel diode is slightly increased from V1 to V2, the potential barrier would decrease because potential barrier is equivalent to now Q times VBI minus V2. Since V2 is larger, the potential barrier width will decrease. Hence, large number of electrons on n side and holes on p sides are generated, and these two holes and the electrons move from one side to other, tunnel through the potential barrier and move to the other side. Because of the increase in the voltage, the overlapping of conduction band and the valence band is increased. In simple words, the energy level of an n-side conduction band becomes exactly equivalent to the energy level of p-side valence band. As a result, because of tunneling effect, more number of flow and hence maximum number of current flows through it. Step 4, applied voltage is further increased. If the applied voltage is further increased to V3, which is greater than V2, a slight misalignment of conduction band and valence band takes place. Since the conduction band of the n-type material and the valence band of the p-type material still overlap, the electrons tunnel from the conduction band of the n region to the valence band of the p region and cause a small current flow. Thus, the tunneling current starts decreasing. Step 5. Applied voltage is largely increased. If the applied voltage is largely increased to V4, then this is how band energy diagram will look like. The potential barrier is given by Q times VBI minus V4. If you see the electrons can no more see the holes on the p side, and the holes on the p side can no more see the electrons on the n side. As a result, you cannot see any tunneling effect and the tunneling current drops down to 0. From now on, you increase the voltage, the electrons will surmount the potential barrier and reach the other side. Similarly, the holes from the valence band surmount the potential barrier and reach on the other side. And it behaves like a normal, from now on, it behaves like a normal p-n junction diode. Now, what are the characteristics of a p-n junction diode? Now, when you see a graph is plotted between potential versus current. When there is no voltage which is applied, then the current flowing inside the diode becomes 0. So, this is the point where you will be seeing it. Now, once the voltage V1 is applied, because of tunneling, there is a small tunneling current which flows into it, and you see that the current starts flowing inside the circuit. Now, the third case is V2, what we have seen. Now, when the voltage is still increasing, the current starts increasing to the maximum extent and goes to the peak. Now, that voltage is called as a peak voltage and the corresponding current is called as a peak current. Now, further you increase your voltage, that is your V3, what we have seen, then we have seen that the voltage As you are increasing your voltage, the current flow decreases. So, you see a point where the corresponding current to that voltage V3 becomes I3 and the current reaches to a minimum point. Then when you apply a voltage, further you increase the voltage, the current is still decreasing and it comes to a minimum point which is called as a valley point. The corresponding voltage to that point can be given as Vv and the corresponding current can be Iv. Further, if you increase the voltage beyond V4, then the the diode starts behaving like a normal diode and the current starts increasing as you increase your voltage. So, in this case, the region where between your peak voltage and your valley voltage, if you see the graph, you observe that the resistance, the slope of the graph becomes negative. That is, my conductance or reverse of your conductance is resistance becomes negative. Now, this is what is important, which is being used as one of the main applications of your tunnel diode. Let us look into the advantages of a tunnel diode. The advantages of tunnel diode are they have a long life, the noise is much lesser and the power consumption is much less. Coming back to the applications of tunnel diode, because of the negative resistance, it can be used in high frequency oscillator. Since its response is very quick and they are used in high frequency oscillators. The second very important applications what I have read is about the reliability. Tunnel diode are very reliable. Can you imagine the tunnel diode found in 1957? Its characteristics still are found to be almost same. Semiconductor device which is found working so reliable, working so good after a very long time is something where you can tell that tunnel diode is the most reliable one. So, in this session we have talked about what is a tunnel diode, what is tunneling effect, what is the symbol of a tunnel diode, what is the working of a tunnel diode, what are the characteristics of a tunnel diode, what is the advantages and applications of tunnel diode. It has been a wonderful joy for me to teach physics and electronics for past 18 years. Completed my summer research fellowship in 2012 awarded by Indian Academy of Sciences at University of Hyderabad. Continuous learning is a quality required by a teacher. I have attended 2 refresher courses in electronics conducted by Osmania University and Indian Academy of Science. I was awarded a minor research project by UGC titled Synthesis and Study of Electrical Properties of Conducting Polyaniline and Nano Metal Oxide Nano Composites during 2015-17. This helped us in purchasing few instruments and continue our research work at our college. I presented a paper in 2014 at International Conference on Materials Science and Engineering in London, which was funded by UGC Travel Grant. In spite of my busy teaching schedule, I completed my PhD in 2017 from Jawaharlal Nehru Technological Institute, Hyderabad. I have published around 15 papers in reputed journals and conferences. I have also co-authored 2 textbooks. One of them is on functional nanomaterial advances in GaN sensing technologies, published by Springer, Singapore. The another one is Analog Circuits and Communications, published by Telugu Academy, Hyderabad. Designing new experiments, collaborating with people, concerned about students' well-being, conducting research and teaching physics is my passion. Thank you.